Okay, electric field. By the way, today's note is mostly filled out for you. So you're barely going to have to write anything in it, especially like except maybe a couple of equations, and that's it. But most of the text stuff is already filled in. So electric field. So a field is simply, whenever you talk about a field, whether in math or physics, mostly physics, I guess, is a region where, around an object where it exerts a force. Okay, so basically, that's why we always call it a force field. Okay, the word force field basically came from this definition. Okay, a field is any region of space, one dimension, two dimension, or three dimension, where a force exerts an effect on some object. Okay, so for example, think of a force field as the ability of a very massive object, if you think in gravitation terms, a planet, to affect an object placed in its vicinity. Vicinity just means surrounding, okay, within its reach. Okay, so the ability of an object to actually pull or push, gravitation obviously would only be a pull or push another object would mean that the other smaller object is in the force field of the big one. Okay, the most important feature of any field is this: the field is always there, regardless of anything near it. If you think about it, if the moon vanishes right now, if the moon actually vanishes right now, does that mean that the Earth has lost its gravitational field, or is it still there? It's still there. It's just that the test mass or the test charge has gone away. Okay, so a field is always there. A field only depends on the object that is the source of the field. But anything else around it is completely irrelevant to the field itself. Okay, you check the existence and strength of the field by placing what? By placing something near its source and seeing its effect. That's why we call it a test charge or a test mass. You put it there and then you let go. The moment you let go, two things are going to happen. You're going to see which way it moves, if it does, and how quickly does it move. Which way it moves, it tells you which way the force acts, and how quickly it moves tells you how much force is on it right at that specific point. Okay? All right. So the physical definition of the electric field of some charge is this: it's the force this charge exerts on a test charge that you actually put at some point from it. Do you think if you place the test charge away from the source charge, away from the source of the field, does it have the same force on it, weaker or stronger? If you get away and away and away from the source. Yes, exactly. So any equation for any field is always distance dependent. It has to depend on how far you are from the source of the field. So in simpler words, you measure the strength and direction of the electric field of some charge by placing a test charge, usually positive, somewhere around it and releasing it to see two things. Number one, where it moves, that will tell you the direction. By the way, if your test charge is usually positive, if your test charge is positive and you release it and you see it move closer to the source charge, what do you know about the source charge for sure? It must be what? And if it moves away, it must be what? Positive. So right there, once you actually set the test charge to be positive, the way it moves tells you exactly what the source charge sign, whether you know it or not. And the second thing is how much it moves, which means how much acceleration is it pushed by or pulled by once you actually release it. So here is the physical symbol for, go ahead, for the electric field. Does anyone know what this letter is called? It's actually in your notes. It's called epsilon. Okay, so again, we can't use E. Why do you think we can't use E for the electric field? Because we already used it multiple times, right? Capital E for energy and small e for what? Pretty much anything that has to do with the electron's charge or the electron's mass. So they had to what? Go to the Greek characters to come up with another alpha, beta, gamma. This is actually the Greek E, which is called epsilon, which actually does look like a very small e. Okay. By the way, there's another way to write this, which is very common in calculus or physics textbooks. It's sometimes written like this, which is probably much easier. Sorry, like this. That's it. So no need to do this. You can just do that. This is a very common way of doing it. Feel free to do either way. Doesn't matter. Okay. So the electric field is a vector quantity. Why is it a vector quantity? Because it's either going to push a charge or it's either going to push it or pull it. So it's either going to result from an attraction interaction or repulsion interaction. Okay, so electric field is a vector, which means it always must have a direction, but we always get around that by doing what? Plus or minus when we choose a positive direction in the problem. Okay, so this is the mathematical formula for what? For the strength of an electric field. So the electric field strength, everyone, the electric field strength is measured by placing a test charge and knowing how much it is, and then measuring how much electric force is on that test charge. This is the defining equation. This is actually one of the most important equations in electricity and magnetism. This is the defining equation of what? Of how strong an electric field is around a what? Is around an electric charge. And by the way, this is also how they define the strength of the gravitational field. Same thing. How do you decide the gravitational field strength? You put some amount of test mass and you measure the gravitational force on the test mass. Okay? So epsilon equals F elec over Q test. In your notes, what does it say next to the second equation? No sign. Exactly. Again, just like with any vector, you're always going to sketch a diagram, or you're always going to have a diagram, which means you're always going to get some positive and negative directions already put on it, which means you do not need signs in this equation. Please do not you put signs here. Okay? All you need to know now is the magnitude of the electric force and the magnitude of the test charge. You divide them up. That gives you the magnitude of the electric field on that test charge. Which way is it pushing or pulling? That's already going to be known from the statement of the problem itself. Okay, so in other words, I never want you to report the epsilon to ever be negative. I always want it to be positive. I always want it to be positive because we just care about the magnitude at this point. Okay, all right. So now let's talk about the what? Let's talk about the unit of it. Well, just like we always do with any unit definition, the way to know the unit of anything is just to go back to the equation and replace the physical symbols with the unit for each one. So since epsilon is equal to force electric, or electric force, I should say, over the test charge, writing each unit where its physical quantity belongs, we get that the unit of electric field strength is newtons divided by coulombs. Newtons measured force, coulombs measure what? Always coulombs measure electric charge on an object or inside of an object. So you either can write it N divided by C, or because it's per, newtons per coulomb. Okay? In other words, it's how many newtons of force are acting on one single coulomb of charge. Okay? How many newtons of force are acting on each coulomb of charge inside or on the object itself. Okay? So for example, what does this mean? What does it mean to say that the strength of some electric field at some point is 432 newtons per coulomb? What does that mean? Someone tells you that if I place a test charge in some point, the electric field strength at that point is 432 N/C. What do you think that means? Yes, Ahmed, give us what you think of that. Okay, each charge, which you mean each coulomb, yes? Mm-hmm. Exactly. Yes. So that means what? If you place a small sphere with 1 coulomb of charge on it, at that point, it suddenly release it, it will move as if someone pushed it with a force of 432 newtons. That's exactly what this means. For every single coulomb of charge, it will be pushed or pulled. By the way, apparently the statement doesn't tell you which way the motion of the sphere is going to be. So you don't know that, but you know for sure that the moment you release it, it's as if someone or the electric field pushed it or pulled it with an amount of force of 432 newtons at that point. Is there a guarantee that this force is always going to be the same at every single point? No. Maybe if you moved it to a different point, it will be 342. or 16 or 1,000. I don't know. Depends. But it just means that every single time you move it, you will get a certain amount of force for that 1 coulomb of charge. Again, what happens immediately after you release it depends purely on what surroundings are around this test charge. And that's why we will never do what we call electrodynamics. Okay, we will only care at the moment of release. What happens after the moment of release, how it moves. This is a very complicated field, requires a lot of calculus because obviously you can tell that the motion is going to be a lot of curves. So that's why it is beyond the scope of grade 12 physics and even first year. The only people who actually study this to very great detail are basically advanced physicists or electrical engineers, because you actually need to know how the charges move in a circuit or on a wire and so much and so forth. Okay, we just care about the moment of release. What happens after, not our concern. This is the only big thing that you have to copy for today, just that. Okay, 30 more seconds. Okay, let's go to the next slide. Okay. To explain interactions between electric charges, whether their signs are the same or, sorry, are opposite or the same, a convention, when you have a convention, that basically means an agreement, has been made. Okay, everyone, again, I did not invent this convention. This convention has been made for the last about 250, 300 years. A positive charge emits or gives out electric field lines, and a negative charge absorbs or takes in electric field lines. If you ever do first year physics, you're gonna sketch a lot of these like this. Yes, so a positive one. You just by the way, this is not something I can give you on like on a test, for example, or something. This is something you need to know. The positive charge is always gonna have what vectors coming out of it, and the negative charge is always gonna have vectors coming inside of it. So always know that the positive one gives and the negative one takes in. Okay, okay, everyone, look, just got a positive charge, and I could move it anywhere I want. If I add another negative charge, the positive does what? Gives, and the negative what? Takes in. Question for you. What if I randomly add a positive charge right here? Let's say in between, but right here, above the plane. Is it ever gonna take in? It's always gonna what? It's always gonna give out. In first year physics, I'm not gonna do it It is technically a requirement of grade 12, but I'm not gonna do it for grade 12. But they will actually ask you in first year physics sometimes to what? They will give you a distribution of charges, and they will basically ask you, show us the what? Show the sum of the field lines around each one. All you have to make sure of that each one of the positives does what? Gets vectors that are coming out, and this one has vectors what? Coming in. If you add another negative charge here, for example, you see how they always move with it? Now you might ask, obviously, which is a very legit question. My first question ever when I saw these things. What's the point of these what's the point of these little arrows like this? Do you see how it kind of looks like a river current that basically tells you how the direction of something moves? Everyone, these arrows actually tell you if you put a test charge, which is always what? Positive. If you put a test charge anywhere in the vicinity of these charges and you release it, how it actually what? How it would move immediately once you release it. So for example, if you put a test charge right here, right here, under the effect of these four charges, the way they're placed, it will be pushed this way. And then it will be pushed this. Obviously, positive charge will go where? Closer to what? Yes, and that's why it will be pushed away from this positive, but closer to what? Closer to this negative. This is basically what they use these electric field lines for, to actually show you the river, or basically the stream of force that's actually going to be acting on any test charge that you actually have here. Okay, so that's basically one of the examples of these websites. Here's another one, positive and negative. What do you think the one for positive and positive will be like? You already have it. Positive and positive. And that's why if you put a charge here, what happens to it? Is there a potential? Is there a potential for a charge in the middle here? Everyone, oops, sorry. If you put a charge right here, a positive test charge here, is there a potential for it to stay still? Think about it. If you put a positive charge right where that red dot is there a potential for it to stay still? Yeah, of course, because it's going to be, if it's positive, this one's going to push it this way, but this one also is going to push it this way. So that means it's going to what? Stay still. Is there any possibility it would stay still here? No way. Why? Because this one is going to push it this way, but this one is going to what? Pull it this way. So again, that tells you if you put a positive charge here, test charge, it will go this way. If you put it here, it will still go left, but it will curve this way. If you put it here, it will curve this way. Think of these as transportation lines. If you put a positive charge on it, it will tell you exactly how it moves. Okay? All right. How about if it's 3? Well, I kind of just showed you what? Just showed you an example. It gets really, really, really complicated here. Question for you. If I just gave you this, by the way, do you have the charges showing or not? No, you don't? All right. What can you tell me about this charge for sure? Why? Exactly, because all of the vectors are going in. So this is negative. What about this one? What about this one? Okay, good. So with the signs, we know for sure. Hold on, don't write anything yet. How about the strength of each charge? Which one do you think is stronger? This one or this one? And you have to tell me why. Like, which one do you think has more coulombs on it or in it? Ammar. Yes. So we're talking about this one, right? Yes. Which one has more line density around it? This one or that one? This one. So this is definitely more positive than this one. Okay. How about this one? We know it's negative, but is it a weak charge or a strong charge? Why? Look how many, if you count the density of the lines coming into it, it's actually bigger than this one and also bigger than this one. The website I actually took this from, they did a simulation basically. This was actually positive, positive, negative, and this was 10 coulombs. So go ahead. This was positive 10 coulombs. What we know now about this one is that this one is positive, but definitely not 10 coulombs. Could be 9, could be 8, could be absolutely anything. They actually had it as 5 coulombs. So the strength of it, or the line density around it, is half. And this one, I believe it was 15. Negative 15 coulombs, of course. Yes. negative 15 coulombs. They give you a lot of these true, false, or multiple choice questions in first year, especially on midterms or quizzes. They just give you the diagram, and then they give you what? What possible combination of charges is possible for Q1, Q2, Q3? And then they give you what? Different combinations of pluses and minuses and different numbers. And you just have to see which one makes the most logical what? The most logical meaning out of all of these, depending on what? Which way the errors are going and how much is the density of the errors coming in or coming out. Okay? All right. Okay. Everyone, pencils down. Let me show you a very easy but actually basic derivation of the what? Of the electric field around a single charge. Now we know now so far one thing about the what? About the electric field around a single charge is that it points which way? Outside if it's positive and inside if it's what? If it's negative. Okay. The question is how strong is the field around the point? Or in other words, if I get further and further and further, how is the field changing? I know it's getting what? If you get further from the source, what happens to the strength? It gets what? It gets weaker. Great. But how? By how much? Like what's an actual equation? Okay. So check this out. Okay. Oh, let's. Okay, forget this one. Okay, everyone, pencils down. Let's actually go through this derivation together. How many charges do you see in front of you right here? Come on. If you really think about this, it will be a very easy derivation. How many charges? Two. Apparently, one of them is very what? Large, and one of them is very small. Which one do you think we're going to set to be the test charge? The big one or the small one? Small one. Even for me, visually, it makes sense because if this one is a large sphere and this one is a small sphere, which one has more inertia? Which one has more, like which one is more fixed? The big one, exactly. So because it's fixed, this is the source, and because this one can move, this is the test charge for sure. Now here's my question to you. On that gray sphere right there, on that test charge, how do you think the blue or the source charge is gonna push it? Into or away? Both of them are what? Both of them are positive, which means if this one is not to move, this one has to move which way? In or out? Out. Okay. So the first thing we're gonna sketch is, I think you have this error, right? Yes, you do. That will be the what? Go ahead. Go ahead. F elect. This will be the force electric or the electric force on this charge due to the existence of this charge and the positivity of the sign. Go ahead. Come on, step by step. Okay, question one. What was the equation for the electric field strength? You already have it. What is it, Ahmed? Epsilon equals F elec over Q test. Okay, do we have an equation for the electric force? Do we have an equation for the electric force between two charges with some distance between them? Who remembers what it is? Again, hint, it's the same structure as the gravitational force equation. K, so K, and then what's on the fraction? Q1 times Q2 divided by, great. So we're going to say, but, go ahead. See, I'm not using Q1 and Q2. Why use Q1 and Q2 when I can just use capital Q for the big charge or the source charge and small q for the test charge? Okay, so the force electric on this charge, pushing it this way or acting on it this way is equal to K. Q times small q divided by whatever d is between them. And don't forget the square. Please don't forget the square. Can I now plant this equation in the top equation? Yeah. Okay. So combining this equation with this one here, go ahead, write this down. Epsilon equals the original F elec, which is here. Who would like to tell me how to simplify this? No more physics. Imagine a grade 10 question. Simplify that. Who would like to tell us what's a good way to write this to really see the simplification going? Other than Ahmed. Otherwise, Ahmed gets it. Anyone else? Imagine if a grade 10 question is saying that thing right here, this thing, simplify. That's all. symbolically simplify. How would you write this down to simplify it first? Ahmed, go ahead. Don't tell me the simplification. Tell me just how you rewrite it. Okay, interesting. Top. So we have a fraction on top. Do we have a fraction at the bottom? If you say yes, you're right. If you say no, technically you're right. You're saying no because it's a single number. But every single number is a what? Is a fraction, because every single number or every single variable has what under it? Has 1. So we can actually write this divided by, like the actual division sign, q over 1. All right. There we go. How do you divide fractions? You have to pay a price and get a reward. The price you pay is that you flip the second fraction. The reward you get is that we don't like division. We like to what? We like to multiply. So that's the reward we get. What's going to happen there? Which q's? Exactly. This q and this q, by the virtue of multiplying and belonging to two different levels, they will actually what? They will actually be canceled out. So can someone tell me what survives? Remember, when you cancel, you don't get a 0. You just get a 1. When you cancel, you get a 1 where things that were in the place of the things that cancel. What survives here? K, capital Q, over D squared. Ladies and gentlemen, that is the what? This is the equation that tells you the what? The strength of the electric field around a what? Around the source charge. What's the Q? What's this Q? Is it the test charge or the original charge? Original. What's the D squared? It's just the what? The distance to the interesting point. What variable washed away? What variable washed away? Like canceled itself out. Do you remember what I told you about the test charge? Does it really matter if you put it inside of the system or you take it out? No. Remember. Always remember what I said at the beginning of the lesson today. If the moon vanishes, that has no effect on the Earth's gravitational field itself. It's just, technically the moon is just a test mass just to prove to us that the field has, so that the Earth has what? Has some gravitational field around it. So always know that the source is the only important thing, and also what? Yeah, okay, here's a math question for you. What happens to this fraction if the distance keeps getting bigger and bigger and bigger and bigger? How many people did limits here? How many people did limits in calculus or function? What's the limit of this equation as d goes to infinity? Basically, as the test charge is placed further and further and further and further from the source. Practically, does the test charge then even feel the source? Why? If this gets bigger and bigger and bigger and bigger, what's the biggest? It's not number. What's the biggest symbol of all? Infinity. What do you get when you divide any number, no matter how big it is, any number, k or q, by infinity? What do you get? Practically what? 0, which makes sense. Because if this gets further and further and further, you should have what? You should feel the strength less and less and less and less. So this equation actually what? Makes sense. What happens if this q gets bigger and bigger and bigger, while the d is kept the same, like the same distance? What happens? What happens if you're standing at the same spot from Ammar, for example, but his charge keeps getting bigger and bigger and bigger? What should I start feeling? More and more what? More and more epsilon, which stands for what? Electric field strength. I should feeling what? I should be feeling more and more and more influence on you, of you on me. Yes. Oh, well, okay. I am, okay, 100% legit concerned. Ammar is saying, I thought that the distance has to be what? Surface to surface. It actually is. 2 reasons. Number 1, these sizes are actually what? Exaggerated, okay? Really, actually, when you deal with charges, you're really dealing with what? With objects usually of the same size, and it's usually a small size. That's number 1. Number two, it is surface to surface, but because anything could be always reduced to a what? a dot or a center of mass. That's why we usually would take it center of mass to center of mass. Make sense? But you're absolutely right. The only time it matters the size of the actual object is only when we do which force? Gravitation, and that's it. With electrostatics or electromagnetics, it doesn't matter. Perfect. Okay, so just to confirm, sorry, the electric field around the source charge, Q in this case, capital Q, does not care about what is around it. This is why you don't see small q or q test in the equation. We just put it there, and mathematically, it cancels itself out. Okay? So everyone, question. If I do what I did on the test, and I don't give you a q test, if I don't give you a q test value, what can you always do? Remember what I did in test number 3 last week? There are 2 questions where I didn't give you a mass. What were the 2 possible choices you could do? Give it any number you want, which is what? Which is the easiest one would be 1, or you know it's gonna what? It's gonna cancel out. Okay? Which is the same effect as if you just put 1. Yes. What does the word uniform mean? We did uniform motion, remember? What is it? What's other words that could stand in for uniform? There's an easier word. When you talk about a uniform solution in chemistry, what does that mean? Say again? Organized. What's an? Say again? Ooh, not quite. Continuous technically has a whole different. Continuous usually means like a function in math. I think you mean homogeneous. How many people have heard of homogeneous or homogeneous in chemistry? Question for you. Do you think this is a uniform solution? Or well, okay, if I forget about the foam on top, is the rest of it a uniform solution? What does that mean? Is every single cubic centimeter of it identical to another cubic centimeter as well? Yes, that's what we call a uniform. Uniform means same or fixed or similar. Is this a uniform field? Is it the same everywhere? No, we just proved that depends on what? Depends on what? Depends on distance. The further you get, by the way, this is how they also what? Symbolize it in first year physics. The size of the arrow represents the what? The strength of the field. And that's why here, you're kind of stronger than here, and if you go. Okay? So this is an example of a non-uniform electric field. This is because at different distances from the charge, you feel different strength. The closer you get, the more strength you feel. The further you get, the less strength you feel, which makes perfect sense whenever you have a source. Okay? Okay, let's do this one real quick. Calculate the magnitude, only the magnitude, magnitude and direction of the electric field at a point located at 2.5 meters to the right of a positive charge, Q equals 6.25 times 10 to the negative 6. Do we have all the numbers we need? What if someone says, what about the test charge? Where is it? What do you say to them? Someone says, I only see one Q. Where's my other Q? Like I only see my source Q. Where's my test charge Q? What's your response to them? One of the many responses you could have. Ammar? One thing you can say, it's going to cancel out. What could be another response? Josh? The test charge is irrelevant because we just proved that mathematically it's going to what? It's going to wash itself out. Perfect. So, but they want it also as a direction. So if I put it here, here's my test charge. I'm going to call it Q, which is positive. And they want it right here. And to put Ammar's and other people's minds at ease, I am putting it from the surface. Remember, does it matter? You will get full marks regardless of the distance. Okay, what numbers do I have? Well, I do have this one to be 6.25 times 10 to the negative 6 coulombs. And how much is this distance? 2.5 meters. Okay, without doing any calculation, everyone, how do you think the electric field of this one is going to point here. Up, down, left, right. Remember, this is a positive source charge. Positive charges do what? Take in or give out? Give out. So if you imagine an infinite number of lines, sorry, an infinite number of vectors coming out, like this, how would the vector here point? To the left or to the right? I know I didn't sketch any vector here, but if you imagine it extending from here, how would it point? To the right. Imagine this vector here is going to extend. By the way, as it extends, does it get stronger or weaker? Weaker, because you're getting further from the source. There we go. That's it. Epsilon. Done. And now we do the math. So what's the equation? Epsilon equals, what was the equation? By the way, you have, everyone, now you have two equations for epsilon. The defining one and the one specifically for a single point charge. Can I use this one? Everyone, can I use this? Can I use this? What do you think? No, I can't. Why not? To get the F elec, I need how many? I don't have two. Also, do I even have a test charge? So that means this equation is correct, but useless at this point. Okay. So we can't use that. What equation do I use? Yes. Exactly. The other one we derived for the specific situation of a single point charge. K Q over D squared. All right. What numbers do we have? Does anyone remember what's K? Small k. It's a very easy way to remember it. It's a big number. And interestingly enough, the number and the power of 10 are the same. 9 times 10 to the 9. That's how I always remembered it. 9 times 10 to the 9. All right. What's my Q? This one. So 6.25 times 10 to the 6 divided by D squared. Well, my distance is 2.5 meters. So it's 2.5 squared. Okay. Let me show you a very interesting thing about this equation. Everyone, look. If you actually square 2.5, if you square 2.5, you actually get what? Nice. So really, this and all of this will cancel out. Well, that's beautiful. What's 10 to the 9 with 10 to the negative 6? 10 to the positive 3, because 9 minus 6 is 3. And it is 9 times 10 to the 3. What's the unit again of electric field strength? Newtons for every coulomb of test charge you put there. Done. Can someone look at the answer in the question? What answer did they get? I mean, we almost got the same thing, but what number did they get? Okay, everyone, I'll come clean here. The actual constant k is actually not 9 times 10 to the 9. It's actually what? 8.99 times 10 to the 9. Okay, but in many physics textbooks, they just use it as what? As 9 times 10 to the 9. Okay, so please feel free always to use it as 9 times 10, although the exact value is actually closer to 8.99 times 10 to the 9. So if you put a test charge of 1 coulomb right here and you release it, first of all, which way would it move? In or out? According to this, if this is positive and our test charge is always by default positive, it's going to be immediately pushed this way. With how much force? How much force? 9,000 newtons for every single coulomb of charge on it. All right. Yes. No such thing. Go. You're absolutely right. So, okay, what's the definition of a coulomb? The definition of a coulomb, for example, is actually what is actually the uh, sorry, what am I saying? Is actually the amount of charge you get, okay, from 6.25 times 10 to the 16 times 10 to the uh, 16, no 19 electrons. Okay, that's one definition. Okay, but the thing about the coulomb actually is that it's defined in terms of what? In terms of other quantities that we'll study more in magnetism, like Tesla, for example, which is the strength of the magnetic field. Yep. But you're absolutely right. Again, usually, do you deal with a coulomb? No, you deal with how much? Yes, very small amount, millis, micros, and now. So you're right. This is a very big charge, a very big force, 9,000 newtons. My weight, not mass. My weight is about 700 pounds. Sorry, 700 newtons. That's 9,000 newtons. That's more than 10 times. You're absolutely right. A coulomb is way too much of a charge. Just so you know, okay, we don't do circuits in grade 12, but we do it a lot in grade 11. Okay, if you remember when we did the Ohm's law, V equals IR, it doesn't take much to actually kill a person as far as amperes is concerned. A single coulomb could actually give you an electric shock. Okay, a coulomb is big. That's why we usually deal with what? Micros and millis. So your suspicion is right. This is way too much force. You're okay. Okay, here's another one. How many charges do I have now? 2. Calculate the electric field at point Z right here due to the what? Due to the point charges Q1 and Q2. And that's it. Okay, do I need to place a test charge there? Do I need to? I mean, could I? Could you always place a test charge? Yeah, everyone, a test charge is something always in your pocket. You always in your pocket have a small sphere of how much charge? 1 coulomb. With what sign? That's your test charge. Put it anywhere and imagine what happens to it. But we don't need to, because we already what? We already invented an equation for the electric field of a what? For the electric field due to a source charge right here. Okay, first of all, what charge is this one? Positive or negative? Q1 is what? Q2. Okay, Q1 is positive, Q2 is negative. So let me show you this. Okay, everyone, do you agree with this so far? Okay. Why not? We're good? No, we're good? Okay. Oh, okay. Yes. Everyone, if I hide this, if this one doesn't exist, how would this charge point here? Left or right? Right there, right here. It would point which way? To the right, because if you imagine this vector extending, but getting what? Getting weaker and weak. I mean, again, this one does not exist. Imagine that we are hiding it. This vector extends, and points this way. All right, we agree. Now, how about this one? Again, if this one doesn't exist, how would the vector here point due to this one? Which way? Exactly, to the left. Because if you imagine this vector extending here and here and here, getting weaker, it would point this way. Okay. So if I hide this one, go ahead. On your diagram, everyone, on your diagram, right here where the green x is, put a vector going this way. What do you think I mean when I say epsilon plus? It's the electric field at that point due to the positive charge. Okay, and now I'm going to hide this one. How would the epsilon negative point. Yes, because the only way that this one would extend is start here and extend this way. Are those two vectors pointing together or against each other? All right, great. So that means what? We're going to have to what? Get the magnitude of this, and subtract them to see which one wins. To see which one wins. Okay, so let's do the math now. All right, so epsilon net equals. Now, it really doesn't matter which one you subtract from which. You can say epsilon plus minus epsilon minus, or epsilon minus subtract epsilon plus. I don't know which one is going to win. Everyone, I have no idea which one of those vectors. By the way, if neither vector wins, what result should you get? 0, which means apparently if you place a test charge right here and you let go, it's not going to move. But I'm going to have a guess that one of these two is going to win, which means the subtraction here is not going to be 0. So let's say it's E plus, sorry, not E, epsilon. Epsilon plus subtract epsilon minus. All right. What are the equations for epsilon? Not the first equation, the second equation, the ones with the K. K Q plus over distance to the plus charge squared minus K Q minus over D. Again, you already have a slide to do this calculation, so there's no need to do it on the diagram. I'm just doing it here because I don't have another slide for this. What's a common factor between these two? K, you're right, K. So K is taken out. Okay, let's put some numbers. Everyone, what is the charge of the plus charge? You have the numbers already. What's the charge of the plus charge, of the plus sphere? Sorry, say again. 5.56 times 10 to the negative 9 in nanos. Okay. How far is the distance of the interesting point all the way to the plus? What do you get when you add 0.668 to 0.332? Exactly. 1, a perfect 1. Yeah, they just played with the numbers to make it like that. So 1 squared minus. What's the charge of the negative charge? Yeah, what's up? Oh, I added, because remember, all of this distance. So this plus that. What's the charge of the negative charge? Here's my question. Are we going to use the negative here? Why not? Thank you. Because we said this equation should be always treated as a what? As a magnitude equation. What's another reason? Did we already look at the minus and pluses of the? Yeah, when we decided which one points which way. So everyone remembers, in these equations, do not bother with the signs. You've already played out with their effects. Great. So no need for a minus. And what's the number? 1 point. Oh, sorry. What's the number? 1.23 times 10 to the negative 9. And what's the distance from just here to here? 0.332. Don't forget to square. Hey, is there another common factor inside of this big bracket? Yeah, what is it? The 10 to the negative what? Which is interesting, because what's the value of k? 9 times 10 to the 9. So if I take this out, it will kill off the what? The times 10 to the 9 part. So, everyone, here's another way to write it. 9 times 10 to the 9 times 10 to the negative 9, and the rest is just the numbers themselves. 5.56 divided by 1 squared, which is really just 1, minus 1.23 divided. Oh my bad. Sorry. This is yes, we're good. 0.332 squared. Who can tell me what's 10 to the 9 times 10 to the negative 9? So no, just this part. Just this part. Just this part. It's 10 to the 0, and any number to 0 is always what? 1. Which, by the way, here's another proof that this makes sense. Can someone tell me what's this rule? What's a to negative b? Come on, you're people who are doing grade 12 functions and calculus. What does this mean? Almost right here. Anything with a negative exponent is equal to what? 1 over the same thing with a what? Yes, you flip, so that's the price you pay, but the reward you get is what? Is you get a positive exponent. So this is, sorry, this is equal to what? 1 over what? A to the b, which means 10 to the 9 times 10 to the negative 9 is equal 10 to the 9 times what? Over, what do you get? That's the proof that anything to 0 is equal to what? 1. It's big. See, you could not understand the 0 trick until you understood the what? The flipping trick. Awesome. So these two technically cancel each other to a 1. So you get 9 times whatever all of that is. Who's got this? Yes, go ahead. Mhm. Oh, okay, you're right. Once I figure out this, apparently I said what? It's E positive minus E negative. So I said this minus that. If I get positive, that means this one does win. If I got negative, that means this one won. Yep. Who's got the final answer? Times the 9. So I'm just going to. So is that the full thing times the 9? Okay. Did you get positive or negative? You got a positive, which apparently does mean what? This vector wins over this vector because I subtracted this guy minus this guy. And if I get positive, that means this one indeed has a bigger strength. How many people got 38 as well, as Ammar got? Just need one more confirmation. Come on, people. Negative. Okay. How many people got negative 50? So apparently, but I don't remember the answer, to be honest. I mean, actually, we can go back to the question and see which one wins. Ah, okay. Apparently, it's negative, or which way? Towards the what? So indeed, it's negative, which means indeed this one wins. Okay, great. So that means negative 50.3 newtons per point what? Oh, 0.4. All right, sorry. 0.4. Which means this one is smaller than this one. This one wins. So what does that mean? If you place a positive test charge here and you let go, which way would it move? Right or left? There you go. You got it. The meaning of the electric field net is which way a positive test charge would move. It would move that way with an amount of force of 50.4 newtons on it. Only if it has how much charge on it? How much? One single full coulomb. Exactly. If you have 50 newtons per coulomb, that will have means 100 newtons per 2 coulombs, and so on. You're right. It's a ratio. The more you go, the more charge you have, the more force you'll have on it, and vice versa. Yes, exactly. And that's today's lesson.